Can you just summarize a little bit of what we covered in the video?
We went over Cartesian vectors. We went over how to get we basically went over position vectors and how to find the total force from using position vectors. We went over a little bit of dot product.
Thank you. Yeah, so we went into more detail on the position vector. So that one we started on week 3. We explained a little bit more and we did some examples with this. You may want to check those. We also talked a little bit about unit vectors, right? We said that a unit vector is simply can be found by taking the vector and dividing it by its own magnitude. We also said that the magnitude of any unit vector was how much? 1. Okay, good. We said that we can express any force in Cartesian notation by simply multiplying the magnitude of the force by a unit vector in the direction of the force. And I did make a note about trying to visualize vectors as products between a scalar quantity and a directional quantity, right? So for example, this force vector, instead of just looking at this and seeing fx, fy, fz, I want you to visualize it as the product of one scalar, this magnitude, times a unit vector. And this is going to help us a little bit when it comes to doing vector operations. And then finally, we introduced the dot product. Now we only introduced it. We didn't really do much work with it. But when we were formulating or introducing the dot product, we did agree that the dot product was equal to the magnitude of two vectors times the cosine of the angle between them. We talked about some of the applications in physics and engineering of the dot product, but we also talked about some of the mathematical applications. Now for this class, we're going to take advantage of the dot product in order to find angles between vectors. That's not the only application, but it is the one that we're going to focus on in this class. Now I'm going to continue where we left off in the video. We talked about the dot product being equal to the product of two magnitudes times the cosine of the angle between them. Now I said that we can use this definition to find the angle between two vectors. If you have defined a vector A and a vector B, then can you calculate their magnitudes? Yes. The magnitude is equal to ax squared plus ay squared plus az squared, and then take the square root of that. Same thing with B, right? That's the Pythagorean theorem. So if you have two vectors defined, then you can find their magnitudes. That means that if you have this expression, all you need now is to calculate their angles. And you can calculate their angles by taking the inverse cosine of the dot product of two vectors over the product of their magnitudes. Now, you're going to think that this is a little bit redundant, because you're going to say, wait, why do we have the dot product here again? We're just going back to the beginning. We're just working in circles. So what we're going to do is we're going to come up with a formulation of this dot product that doesn't depend on the angle. And hopefully that way we can express the dot product in two different ways and use it to find the angle. Now for the students on that side, I apologize, but the camera is only recording this board. So if you want, you can move to this side, or if you can see well from there, then that's perfectly fine. But I'm not going to use that board because the camera isn't recording it. And I want this for my online students as well, so they can see it. So let's look at that formulation. This is going to take a while. We're going to be writing a lot of variables here. So I'm going to ask for your patience, but I do want you to play an active part in this formulation, because I don't want to just solve it all by myself. Let's define a vector A in Cartesian notation. How can I define my vector A in Cartesian notation? Well, what would that look like? Cartesian notation.
X, Y, Z.
Okay, right? We have an x component multiplied by a unit vector in the x direction, right? We have a y component, and we have a z component. Now we can do the same thing for a second vector b, right? What would that Cartesian notation look like?
The same thing, just for B.
All right. And now if I ask you to calculate the dot product between these two vectors, What I'm essentially asking you to do is to take the Cartesian notation of the vectors and dot them to each other. Now, this particular problem is going to take a lot of space if we use 3 dimensions. So for the purposes of this formulation, let's say that we're only working on the xy plane. So we're only looking at the xy plane. We have a vector A and a vector B. We want the dot product between these two vectors. If we're only looking at the xy plane, we can say that the z component is 0. So AZ equals 0, BZ equals 0. And this will make our lives a little bit easier. When you're taking the dot product between two vectors, you can think of, again, vectors as products of scalar quantities and directional quantities. Now, why do I want you to do that? If you consider these vectors as products, you have a scalar quantity multiplied by a direction, scalar by direction, scalar times direction, then you can treat all your scalars as regular numbers. So that means that the dot product is simply a multiplication of 2 regular numbers. So let's do that. When you're dotting these 2 vectors, essentially what you're doing is you are multiplying them. Do you remember how to multiply 2 expressions that have multiple terms? How do we do that? Distribute, right? So we multiply this by this, right? And then we add it to the product of these 2, right? We do the same with this. Is that correct? Does that look right? Okay. So let's go ahead and solve this. We have, and again, this is going to take a while. We have AXI times BXI. What does that give me? AX times BX. But we need to consider the i's. I can't really say I squared because this is not a scalar quantity. This is a directional quantity. But instead of I squared, I can say I dot I. So the scalars, I'm multiplying them because they're numbers. They're real numbers. The directional quantities, I'm still dotting them because they're still vectors, right? So that's why I want you to think always of vectors as separating the magnitude, the scalar, from the direction. So we can treat them differently. What's the second term? Can somebody read the second term to me? This plus what? What's next?
AX
BY.
times BY.
Thank you. And then what are my vectors here?
I dot J.
Thank you. Third term, we have AY times BX, I dot J again. And finally, my fourth vector, we have AY times BY, J dot J. Now you may be thinking, where does that leave us? We still have these dots to take care of, but it's okay. It's okay because we still have this definition of the dot product to help us. We already defined dot product as the product of 2 magnitudes times the cosine of the angle between them. So let's look at what this turns into when we actually apply the dot product law. So we have AX times BX times I dot I. We say the dot product is the product of their magnitudes times the cosine of the angle between them. So let's start with the first I. What's the magnitude of I?
1.
Okay. What's the magnitude of I?
1.
I and I are the same vector. What's the angle between them?
0.
Okay. Oops. 0. Does everybody understand this? Okay. We go to our second term. We have AX BY. Again, magnitude of I1, magnitude of J1. So I got 1 times 1. What's the angle between the I vector and the J vector?
90 degrees.
Okay. Cosine of 90 degrees. We repeat the same thing for our third vector, or for our third term. And we repeat for our fourth term. And now, I hope that you're realizing that this is actually going to simplify a lot. Because we have AX times BX times 1, no change, times 1, no change. What's the cosine of 0? 1. So this is just AX times BX, right? And what we did here is we eliminated the vector, the directional portion of this term completely. So we have ax times bx. Cosine of 0 is simply 1. Ax by 1, 1. What's the cosine of 90?
0.
Cosine of 90 is 0, so what happens to this term? It goes away. Cosine of 90, cosine of 0. Okay? So what does this leave us with? We have the dot product of two-dimensional vectors, A and B, is equal to the sum of the product of the x terms with the product of the y terms. If these were three-dimensional vectors, if we would have added an additional AZ term, we would have had the same equation, albeit longer, and then we would have ended up with AZ times BZ. So this is good, because what does this tell us about the dot product? Is the dot product a vector or a scalar? Scalar. Has no directional quantity. So the dot product essentially takes two vectors and transforms them into a scalar quantity. And that's really good, because if we eliminate the directional component, then we can solve this dot product without needing to know the angle. So now I can say that if I can solve the dot product without necessarily knowing the angle, then I can use it to calculate the angle between two vectors. Because now we know the angle between two vectors, I'm just going to copy it from over there, is the inverse cosine of the dot product between A and B. But we already know that the dot product is simply the sum of its individual rectangular terms. So AX, BX, AY, BY, AZ, BZ, divided by their magnitudes. If you know AX, BX, AY, BY, AZ, BZ, can you calculate these two magnitudes? Yeah. We can make a longer expression, right? But we're not going to do that. Essentially, at least for this week, we're going to try to use the product to calculate angles between vectors. So if we have two directions, two vectors, two directional vectors, then we can calculate the angle between them. This is going to help us a lot when we're dealing with different forces acting along different lines. Okay? So that is a bit of a formulation to use the dot product to calculate an angle between two vectors. Before we start working on an example, are there any questions with this entire formulation? If we're looking at four-dimensional vectors, right? So we have an additional term in the fourth dimension. Could you calculate the dot product? Yeah, exactly the same thing. Okay? So as long as you know how to calculate the dot product using only its scalar quantities, then you should be able to use it to find the angle between two vectors. So now, let's start an example. Let's work with problem F225. But we're not going to solve it completely now. We're going to solve part of it. Then we're going to do a little bit more theory and then finish solving the problem if we have time. So this is problem F225. Now if you have your book, I recommend that you look at your book, because I'm going to try to draw it, but I'm not really sure I'm going to draw it very nicely. This is a three-dimensional problem, so I'm going to have to try to draw a three-dimensional figure. So F225. So we're looking at three-dimensional space where I have my x-axis, my y-axis, and my z-axis. When I say three-dimensional space, try to consider this as an orthogonal view. So I'm kind of looking at these axes kind of from above, a little bit from above. But essentially I have my x-axis, my y-axis, and my z-axis. And I'm going to call my origin O. That's a typical name for origin. We call it O. Before I keep moving, what are the coordinates of O?
0, 0, 0.
Yeah, O has coordinates of 0, 0, 0. And I'm going to define a point A that is located at an x distance of 1 meter, a y distance of 2 meters, and a z distance of 2 meters. So this is my point A. Again, if you can look at it on your book, it may be more helpful than trying to figure it out from my drawing. What are the coordinates of A? 1?
1, -2.
There we go. -2, 2. Remember, positive y, negative y, right? So 1, -2, 2. So we have the 2 points, A and O. We have two points with their coordinates. And now, I'm going to have to move some things a little bit. I'm going to apply a force vector at A. I'm going to apply a force vector. I'm going to say that this force acts on A. And I'm going to define my force vector as -6i plus 9j plus 3k kilonewtons. So I have this force vector acting along A. Okay? My question to you will be, I have a force vector. It's defined in Cartesian notation, which means that you know its x, y, and z components. But now I would like to find the angle between this force and this imaginary line along AO. So if we draw a line, we draw an imaginary line from point A to point O, I want you to tell me what the angle between my force F and my line is. With this information that I've given you, can we solve this problem? What do you think? Is it solvable? What do you think? Maybe? Unsure. Okay, so 1 yes, 1 unsure. What do you think?
I think so.
Okay, so 2 yeses, 1 unsure. All right. So let's figure out if we know, or if we can solve it, or if we need more information. How would you find the angle? That's the end goal, right? The end goal is to find the angle. How would you find it?
You need to find the vector from A to the origin.
Exactly. William, right? Tyler?
Either one.
Either one? Okay, William, Tyler. Yeah, we need to find a vector that goes from A to O. What do we call those vectors? The vectors that denote distances, or I don't want to say the actual word, but vectors that denote, there we go, position vectors. I was going to say, what do we call the vectors that denote positions, but that would have been too easy, okay? So we want to find the position vector from A to O or O to A, William?
From A to O.
From A to O, okay. Good. So let's find that vector. How do we find that vector? We have 2 points. We have their coordinates. So let's just write them down. How do we find a position vector?
Point from the second point minus the first point.
Okay, so let's start with the x-coordinate. The x-coordinate of my second point would be 0 or 1? 0. Okay, so 0 minus 1 in the x direction. 0, and here's a little bit tricky, right? 0 minus -2 in the y direction.
And then 0 minus
In the z direction. This position vector has units because this 3D space has units. So what would the units of the position vector be? Think, here we're measuring 0 and here we're measuring 1. 1 what? Meters, right? So my position vector will have units of meters. If you're unsure where this unit comes from, remember that we're measuring 1 meter, 2 meters, 2 meters. So we're going to have meters here, 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 and here. And we just factor out the meters term. Okay? So we have our position vector. I'm going to write here -I, right? Plus 2j minus 2k meters. And now I can draw my vector here. Now, quick question. My position vector, Is it going to go in this direction or in the opposite direction? From where does it start? A, okay, and it ends at O. So this is my position vector from A to O. I know this is from last class's material, but are there any questions with this position vector? You all know where we found it, how we found it? If I give you another one, could you find it? Okay, good. So we have our position vector, and now what? You already said something. Let's try someone on this side of the classroom. Now what? There's three of you. Any one of you three can answer.
Find the, like you have R.
Okay. We can find the unit vector, and I think we could do that. I'm not really sure why. Because remember that we want to calculate the angle between them. We could find a unit vector here and calculate the angle between this unit vector. However, is that really necessary? Or can we just go straight to calculating the angle?
Find the dot product.
Okay. We can find the dot product simply using this one. Your answer is not wrong, right? It's just that it's a little bit of some extra steps. However, we will go back to that later in just a second. So we can just find the dot product, right? So let's find the dot product between my force and my position vector. Dot product is defined as the product of the magnitudes times the cosine of the angle. But wait, I don't have the angle. So how else can I find the dot product? If I don't have my angle, what's another way of finding this dot product?
With RAHBH.
Okay. Okay, so let's do that. It's going to take a while, but let's just go ahead and do that. In addition to using this formulation, we can also multiply the individual x, y, and z terms of each vector and then add them up. So what would that look like? We have fx times rx. What is fx? Rx? Okay, so we are negative 6 times negative 1. And this, we add fy, ry. What is fy? Ry? And we can do the same thing with the z direction. What's fz? Rz? Thank you. Good. I'm missing an important thing, right? We can't forget about our units. So what are the units of the force vector? What about the position vector? Okay. So the units of this dot product will be equal to the product of the units of the individual vectors, in this case, kilonewtons times meters. Can somebody solve this for me? We got 6 plus 18 minus 6.
18.
Thank you. Units?
Kilonewtons.
There we go. That's not really what I asked for, but it does take us a couple of steps closer, right? We found the dot product between the two vectors. Now we can use this to calculate our angle. The angle was inverse cosine of the dot product over the product of their magnitudes. So we have the dot product. How about we find the magnitudes of the vectors so we can take their products? Let's start with the magnitude of the force vector. How can we calculate that magnitude?
Square root of each one squared.
So I'm going to go ahead and write this on the board, but if you already have it, just try to calculate it and give me that value of that magnitude. See, we got square root of 36 plus 81 plus 9. How much is that? $11.2 kilonewtons. Does that sound right? to everyone else? Okay, good. Let's look at the magnitude of the position vector. Now here, if we would have gone with Drew, right? If we would have gone with Drew's recommendation of finding the unit vector, then this would have been a little bit easier, right? Because what's the magnitude of a unit vector? 1. But since we didn't, we're still going to have to calculate this position vector's magnitude. So we calculated the same way we calculated the magnitude of the force vector. So can somebody plug those numbers in and tell me the magnitude of this position vector? Sorry?
3
Units?
meters.
Thank you. Good. We have the dot product of two vectors. And we have the magnitudes of those two vectors. Can we now calculate the angle between them? Or do we need something else? Is this enough to calculate the angle? You're saying yes? Okay, so let's go ahead and calculate it. Can you give me the equation to calculate an angle between two vectors?
Cosine inverse the dot product of the two vectors
Okay.
over the magnitude of each vector times each other.
Like this? Okay. So we've got inverse cosine of 18 kilonewtons times meters divided by 11.2 kilonewtons. If you have it on your calculator, then don't round, right? Use the number from your calculator. Well, I don't, so I'm just going to round. Times 3 meters. What happens to the units here? They all cancel out, right? It's good because our angle is going to be in degrees. So our units are going to cancel out. We're going to get inverse cosine of 18 over 11.2 times 3. How much is that? Let's use degrees this time.
37.6 degrees.
Can somebody confirm that value? Yeah, good. So we found the angle between my force vector and my imaginary line, given 2 points and the force vector itself. So that's good, because at least you knew that we had to convert that line into a vector by using the position vector. And then you knew how to apply the equation for the dot product in order to find that angle. Now I want to go back to Drew's recommendation of using the unit vector. Now unit vector is a very important quantity, and if you saw last video, you'll see why, right? It helps us to find projections of forces along lines. And I want to go to that. I want to use or combine what I know about unit vector and what I know about a dot product in order to find projections of vectors. Now when I say projection, what do I mean, right? When I say projection, I'm talking about the component of a vector along a line. If that doesn't click with you, think of it in terms of right triangles. So let's say I have a vector. Give me a letter.
Z.
A vector z. When I say that I want to find the projection of my vector z across the x-axis, essentially what I'm asking you to do is I'm asking you to give me the horizontal component of this right triangle. Okay, that's all I'm doing. If I'm asking you to find the projection of z on the y-axis, I'm just asking for the vertical component of this right triangle. Now I've mentioned before, I don't like using the terms horizontal, vertical, so I don't want those to stick into your heads, because sometimes, especially when we're dealing in 3D space, vertical may mean something else. In this case, we're saying horizontal, vertical, because that's all we have. But I want you to get the idea that the projection is essentially what happens when you project. So if I'm standing on top of this vector and looking downwards into the x-axis, this is what I'll see. That's how long of a vector I will see. Projections are very fun things to study. They are more research for multivariable calculus, so stuff you will learn in Calculus 3. but it is fun. Go ahead.
One term that my last static professor said was like the shadow.
Yeah.
Like
Shadow
if
is
you're
a fun.
shining a
Yeah.
light down, it's the shadow that it would cast.
That's exactly right. And this is very good, right? Because the angle or the inclination of this axis is going to determine the length of your projection, right? That's a really good term. So when I say projections, the easiest way to look at them is thinking in terms of x and y axes. However, I don't want you to think that projections are limited to only x and y axes. In fact, you can take the projection of a vector along any axis. It doesn't even have to be x or y. It can be an arbitrary axis. We came up with a way of using the unit vector, right, to convert a force into Cartesian notation. That was in the last video. Now we're going to see how we can use those same unit vectors to find these projections of a force along any axis, not just an x-axis, not just a y-axis. So I'm going to explain how to do that by drawing a simple vector A. Now we have vector A, and vector A is located at an angle of theta from an arbitrary line. Now I'm drawing this horizontal so that it's easier to visualize, but don't think of this as the x-axis. Think of this as any arbitrary axis. Okay? Let's give this axis a name. What can we call it? Not x.
T.
T, all right? So we have our vector A, and vector A is located, or it's pointed at an angle of theta from my axis t. T can be any direction. I'm drawing a horizontal for simplicity, but it can really be in any direction. Now what I want to do is, if I ask you to find the projection of vector A along this line t, right? And if I ask you to draw it, to draw that projection, I can't really give you the marker for you to draw, so we're trying to keep our distance, but what would you draw? What's your name in the back?
Chris?
Chris, what would you draw? If I ask you to draw the projection of A along T. In fact, I'm going to draw it and you tell me in which direction and when to stop.
I guess to the right.
Okay? Tell me when to stop.
Stop.
Okay. So the projection of A along T is essentially like, what was your name? Hunter. Like Hunter said, the shadow, right? You shine a light from the top, you have this projection. I can call it A sub T, and that's typically the name that you'll find. However, I want to speak not in terms of the axis itself. I'm going to call it the angle or the projection, the vector, parallel to my t-axis. Because we have a vector A, we want to find how that vector A projects along the t-axis. So my vector, or my projection vector, is simply parallel to my t-axis. You can call it A sub t if you want, but I'm just going to call it A parallel. And you'll see why in a second. Okay? Now, let's say that instead of dealing with vectors, let's say that we only know their magnitudes right now. We only know their magnitudes and the angle. In terms of magnitudes, how can I calculate the magnitude of this projection, given the information already on the board? Okay, say it louder.
Use cosine.
Exactly. The parallel vector will have a magnitude of my vector A times cosine of the angle between them. Does that make sense so far? Because that's essentially what we're doing. Remember, when you have a right triangle, and that's what we have here, a right triangle, cosine is equal to adjacent side over the hypotenuse. Adjacent side over the hypotenuse. Multiply both sides by the hypotenuse and you get this equation. A parallel is equal to A times cosine of theta. That is the magnitude of my projected vector. And here is where things are going to get interesting. Drew likes unit vectors. Andrew. Drew or Andrew? Just Drew. Sorry about that. Drew likes unit vectors. I don't know why, but he likes unit vectors. He always wants to calculate them. So let's calculate a unit vector along my axis. So I'm going to have my unit vector along my axis t. What was the magnitude of this unit vector, Hunter? Just 1. And the direction will be just the direction of t. If you know at least 2 points on this line t, can you find this unit vector? Yeah. You use the 2 points to create a position vector. Then you divide the position vector by its magnitude and you get this unit vector. Okay? So, if we have the unit vector and we know that this is the magnitude of the parallel component, we have something interesting here. Because if I were to give you, right, the dot product, or to ask you to calculate the dot product of A and the unit vector, what would this look like? Just the general definition, not the long one, the short one that we started with. What's the general definition of the dot product?
A times ut cosine theta.
Like this? Okay. And what is the magnitude of A? Just A. Let's just call it A. What is the magnitude of ut?
1.
And then we have cosine theta. So this is just A cosine theta. Now what does A cosine theta represent in that figure?
The bottom line.
Yeah. Just the magnitude of the parallel vector. That means that the dot product between a vector and a unit vector along the direction I want is simply equal to the magnitude of the projection. And that's good. We're not done yet, right? We have the projection magnitude, but we need a little bit more because we want the vector, not just the magnitude. But now I want you to rewind a little bit to last class, yesterday's class, where we said that if we have the magnitude of a vector and we have a unit vector along that direction, we can find the vector itself, right? How did we do that? Do you remember what was the procedure?
We multiplied the magnitude by the unit vector in that direction.
Exactly. So if I want to find the vector form of my parallel vector, I just have to multiply the magnitude times the unit vector along the direction that I want. Is that correct? Good. And now, here's where it all becomes very fun. This magnitude is simply the dot product. Now let's say that I have my vector. I have 2 points along my side t. I don't really have time to calculate the angle, but that's okay because this A cosine theta is simply a dot product. And if you don't know the angle, can you still calculate the dot product? Yeah, by multiplying its x, y, and z terms and then adding them up. So what this means is that we can use the dot product for a variety of purposes, right? One of those purposes is to actually find the angle between vectors. But another purpose is to find projection vectors. If I give you an angle A, and I give you any arbitrary axis t, and I say find the projection of A parallel to t, all you have to do is take the dot product of A times a unit vector, and then multiply it by a unit vector, and that's your projection. There's like different ways for me to write this equation, right? And you're going to use whichever one works best for you. If I give you the vector and the angle, maybe this is better. If I don't give you the angle, maybe it will be better to just find the dot product first and then multiply by the unit vector. Whichever way works better for you. You can find this dot product, again, by multiplying the x terms. Ax, ux, right? Ay, uy, az, uz. And just multiply by the unit vector. So whichever formulation you prefer, I would just use the one that's easiest for me. Any questions with this? We're going to do a problem, so don't worry about actually applying this. But for now, are there any questions on how we got to this or what this means? So we have two important applications of the dot product. Of course, there are many, right? I mentioned last time that in physics, we use a dot product to calculate work. In engineering, we use a dot product to calculate power, right? But here for this class, we're going to use a dot product for more mathematical operations, such as calculating angles and calculating projections. And now, here's why I'm using the word parallel. If I know a vector and I know its parallel projection, then I can say that I know its perpendicular projection as well. Because I have what's essentially a right triangle. If you know this magnitude and this magnitude, can you figure out this magnitude? Yeah. Also, what I have is the sum of two vectors. Remember, triangle rule. You have that the sum of two vectors is essentially equal to placing one vector and then drawing a next vector after it and creating a triangle with it to find the hypotenuse. So the vector relationship here is that A is equal to parallel vector plus the perpendicular vector. And if we're speaking in terms of magnitudes, then A squared is equal to A parallel squared plus A perpendicular squared in terms of magnitudes. Any questions with this? You're going to notice that as we move on, as we move forward with this topic, you're going to stop seeing me and you're going to stop seeing the book ask you for X projection, Y projection. Instead, we're going to start giving you arbitrary axes. And we're going to stop asking you to find shadows or projections. We're going to say find a vector perpendicular to this axis. Find a vector parallel to this axis. Find a vector projected at a 25 degree from this axis. So the idea behind this is not to throw all these equations at you and just let you use them. The idea is for you to understand how this works from a general form. So don't think of this as strictly horizontal. This axis could be a vertical axis. What matters is that you know this vector and you know at least 2 points in the axis to find the position vector. There are different ways of expressing lines. I think you may have learned from your math classes that you can also express lines with equations. So I can say find the projection of vector A along a line represented by the equation y equals mx times ms plus b, right? So it's up to you to figure out how you formulate this equation, but these are the basics, right? With these basic terms, you should be able to solve any problem. Does this class end at 7:15 or 7:45?
45.
Oh, we still have a lot of time. Good. Let's go back to this example. We found the angle between force and my imaginary line AO. Now, I would like for the projection of that force vector along this line AO. Okay? In other words, I want the force vector that's parallel to this line. Given this information, can we find that force vector, that projection that's parallel to line AO? What do you think? Hunter says yes. What do you say? Yes? Nice. What's your name?
Chris?
Chris. Thank you for volunteering, Chris. How do we start? Well, I want to find the projection. First off, they gave us force, right? We have a force, and here's my force vector. Second of all, we know the direction of this line. Can somebody remind me the position vector for this line? So we can have it here as a reference.
-1, 2, -2.
Thank you. So we have a force. We have the line, expressed as a position vector. What do we need to find the projection of that force along the line? First of all, what's the first thing we should calculate? And if you don't remember what's the first thing we should calculate, think about Drew. What does Drew like?
Drew plus
Unit vectors, right? So the first thing we should calculate, just ask Drew, unit vectors. How do we find that unit vector? That's the magnitude, right? That's the magnitude of one of these vectors.
Oh, and then
But how do we find the vector itself? Exactly. Right? Hunter says we can divide the vector by its magnitude. Does everybody agree with him? Yes? Okay. So we divide what vector? Do we divide force vector by its magnitude? This is my unit vector along this line. So which vector should I use? What? R. Thank you. So we already know that the position vector is negative I plus 2j minus 2k meters. What was your name? All the way over there. Leslie, what was the magnitude of the position vector?
Square root 9, so it's 3.
Exactly, right?
When we're doing this, we don't have to use our negative signs, right? Because it's
They're gonna square out anyway. So in last class, one of the issues we had is that keeping in mind that these were gonna square out, some students forgot about this negative sign, right? So I just write it for completeness. We don't have to worry about them because they're gonna square out and become positive, but you cannot eliminate these negative signs, right? Okay. So what was this? 1, 4, 4. That's 9, right? So the magnitude of the vector was okay. So what does my unit vector look like? We have negative 1/3 I plus 2/3 j minus 2/3 k. Now, if you are writing this on paper, try to keep it in fractions, right? To avoid rounding error. Because 1/3 is 0.333, right? If you just write 0.33, then here 0.67, then 0.66, then you're going to start to have a little bit of rounding error there. Okay, so just keep it in fractions if you want. We have our unit vector. What are the units?
Meters.
What are the units of the unit vector? Look at this expression. What's happening here? Right? Unit vector has no units, no dimensions. Let's say that you got all the way to this point. You're not sure if your math is correct. How can you check if this is a unit vector?
Dimensional analysis.
swirled.
But there are no dimensions to analyze, right? So there's something else.
Swirled, and then that'll give,
And what should that give?
and that'll give you 1.
Exactly, right? We find the magnitude of this unit vector. It should be 1, right? Because it's a unit vector. So I'm going to assume that it's correct. But if you're ever unsure, you get to that point, you don't want your final answer to be wrong, double check that unit vector. Good. So we found our unit vector. What else do we need to create this projection?
We need the projection of F onto the.
Okay. And how do I find that projection? I'm going to call it F parallel or FAO, whatever you want. How do I find it? How do I find any vector if I have a unit vector?
It's the unit vector times the magnitude.
Exactly. Any vector is equal to its magnitude times a unit vector in the direction that I want. In this case, my unit vector is AO, which I already have. All I need now is to find its magnitude. How can I find its magnitude? There's different ways. There's multiple ways. Let's go with the easy one. Do we have the angle between them?
Yes.
Okay, so should we just use that? Okay, so what's the magnitude of my projection?
Times cosine theta.
Okay. Like this. Okay, do we know F? The magnitude of force, do we know it? Did we calculate it?
Not yet, but we could.
Okay. Did we calculate it in the previous part? Okay, so we have it. Do we know theta? Okay, we calculated it already. Do we know the unit vector? Yes, it's right there. So can I solve this? Yeah, so let's go ahead. What's the magnitude of F? It was 11 point something?
11.22.
What's the angle?
57.6.
And then we have our unit vector. All right. This will give me a vector with the following x, y, and z terms. Somebody just calculate it and give them to me. Yeah?
So why does our unit vector not have units? Like, I understand mathematically it cancels out, but like, why would it not?
Because a unit vector only represents a direction. That's all it's supposed to represent, right? So I'm not really sure how to explain it physically, which is where I'm failing, but the unit vector essentially is a direction. It's not a, yeah. So there's, in mathematics, well, in engineering, there's a tendency for us to always define what we call unit values, not just vectors, widths, depths, which are simply mathematical. They're purely mathematical. They don't represent physical entities. They're simply mathematical entities with some scale of 1. And the reason we use the scale of 1 is so that it doesn't modify this magnitude. So physically, the best I can do is say that a unit vector is only a direction. You shouldn't see it as one something along the line. It's only a direction. That's all it is. Yeah. Because f is what eventually gives it its dimensions, right? William said earlier to do a dimension analysis. For this one, I don't think it's necessary because there are no dimensions, but when we are doing dimensional analysis, we will see that in order for an equation that has the unit vector to be physically quantifiable, unit vector cannot have dimensions. It simply cannot. I like to think of it like radians. You know radians? For me, radians is simply quantified as some sort of length, right? Some sort of length along a unit circle. But radians actually doesn't have any units, any dimensions, right? So when you see things like frequency, which is radians per second, really is just 1 over second. And it's kind of hard for me to visualize that because I always want to ascribe a dimension to something. But there are very real things that don't have dimensions. So frequency is one example, electrical or wavelength, right? So yeah, it's kind of hard for me to explain it, but that's the best I can do.
Okay.
Hopefully you're getting your money's worth. But anyway, what is this force vector?
I got -2 I hat plus 4 j hat minus 4 k hat.
It's actually pretty clean, right? I was expecting something a bit more complex. What are the units?
Are we still in kilograms?
Yeah.
Nothing else has.
Yeah. Cosine of 57.6 doesn't have units. The unit vector doesn't have units, so my only remaining units are kilonewtons. Okay? If this is not a satisfying answer for you, you can also find it by finding, well, you know that f cosine theta is also the dot product of f and the unit vector, right? So that's another way of finding it. I'm not going to solve it here for you, but if you do the dot product of f and the unit vector, so if you multiply -6 times -1/3 plus 9 times 2/3 plus 3 times -2/3, add them up, multiply them by the unit vector, you're going to get exactly the same number. So yeah, different ways of solving them. You pick the one that's easiest for you. I think that if you look at the solution for F225, it's in the back of the book, it's not going to do it this way, it's going to solve it this way. And that's okay. That means you have different ways of solving the same problem. Any questions? If I were to give you a test on the position vector, the unit vector, and the dot product, could you solve it? You're saying?
Need some more practice. So.
Okay, a little bit more practice. Okay, so let's do that. Let's just do a little bit more practice before this class ends. We still have 20 minutes, so let's practice a little bit more. What about you, Chris? Would you get 100 on the test?
100.
You gotta aim for 100, always. Aim high. So let's do 230, F230. I mentioned it in the last class, I'm gonna mention it again. The reason I like these fundamental problems is because they focus on like one thing at a time. So they're going to test your knowledge of the material that we're covering, not necessarily your knowledge of geometry and other things. That's not to say that geometry isn't important. It is. It's just a prerequisite, right? So if you're going to fail in this class, hopefully you're going to fail because you didn't understand statics, not because you didn't understand geometry. So that's my hope, but we'll see. So F230, this one's actually hard to draw as well. So I'm going to try my best to draw it, but you can look at it in the book for reference. It's really weird seeing your face because I had no idea you had a mustache. So it's, yeah, I guess I have like a mental picture of what all of you look like, which is probably very different than what you actually look like in real life. Maybe you're all ugly or something, who knows? Anyway.
Which is sad.
It is, it is. I'm actually beautiful inside behind this mask. You just don't know it yet. If I take it off, you'll be like, wow, this guy's amazing. I'm kidding. Let's do F230. We have an XYZ axis. I'm going to draw my x-axis, my y-axis, my z-axis. My z-axis doesn't have to be that long. Okay. We have our origin. What are the coordinates of the origin? Yeah. And we have a rod or a pole that starts at the origin and ends, let's see, -4 feet from the x-axis, 4 feet towards the y-axis. Let's see, 4 feet. Again, you're going to want to look at this on your book. At 4 feet. About 4 feet. And then 2 feet from the z-axis. Okay. So here is my pole. Oops. All right, so you have this rod thing that's located from the origin to this point. Now, I don't want to rely on my artistic ability, so instead let's use coordinates. What's the coordinate of the end of the pole? I'm going to call it A. What's the coordinate of this point?
-442.
I think that's a better way of seeing it, right? Because that way you don't have to worry about understanding the drawing itself. You just know the coordinates yourself. Okay. Then we have a force that acts on point A, but in another direction. So we have force with a magnitude of 600 pounds acting on point A, but in a different direction. And to nobody's surprise, we're not given the force in Cartesian coordinates. Instead, we're going to have to find those coordinates ourselves. All right, so I got my point A, I have my force. Let's see. I'm going to draw a line that represents my y-axis. This line is parallel to the y-axis. And from this line, on the xy plane, we have a 30-degree angle. So this is the xy plane. And from that 30-degree angle line, we have an angle of 60 degrees that leads us to the force. Is this understandable? If it isn't, you have your book. Let me see if I can project it over there. What? Probably a similar one. I think for the homework I didn't assign fundamental problems, so it was probably a similar one, maybe the same drawing, but probably asking for different things. Right projector. Yeah. So it's 230. So hopefully this drawing will make it a little bit more understandable. All right? And now the question is to determine the components of the force acting parallel and perpendicular to the axis of the pole. So we're going to use the dot product, right? And we're going to use it to find that wretched parallel component as well as a perpendicular component. We have 15 minutes. Let's try to solve this problem in 10. If we can solve it in 10, then I would say we're almost ready for the test. If it takes longer than 10, I think we need to study. Well, not me. You need to study. So how do we start this problem? And I want everybody to participate because it's a pretty small class. So I don't want just Hunter answering everything. So let's start with you. How do we start this problem? What would you do? If this was a test, you have 10 minutes to solve this. Then the test closes.
All right.
It's pass-fail, no partial credit. What do you do?
You'll find the x, y, and z coordinates of the force.
Okay, so we want to express my force in Cartesian coordinates. Is that correct? Is that what you're saying?
Yes.
Good. Thank you. All right. Thank you for that. Thank you for giving me a pathway. Chris, how do I start? Which of these can I find first? Or which of these is easiest to find first? Don't worry about getting the answer wrong. I mean, half of us don't know the answer anyway, so just give it your best shot.
I would say Z because
Okay. Let's do that. FZ. So Chris is saying that it's easier to first start with FZ. What is FZ? You're right. You found the right angle. That's good.
inverse tan 60? Or no?
Not quite.
No?
We're looking at a right triangle here,
Oh, yeah.
right? So remember that we're looking at essentially a right triangle. So what would FZ be? No need for sines, or sorry, no need for tangents yet. If I were to project this, essentially what I'm looking at is my 600-pound force, and then FZ here, and then FXY here. So it's just the component on the XY plane. And this angle, like you said, is 60.
Oh, okay. So it's 600 sine
Mm-hmm.
60?
Correct. That is correct. FZ is 600 times sine of 60. Don't forget the units. Pounds. Can you give me that number? While you do it, can you give me that number? Units. Don't forget the units, okay? Good. So we found FC. And notice that when we found FC, we also got an XY component. Now, when I say FXY, notice that I'm not really saying FX. I'm not really saying FY. Instead, I'm talking about the component of the force on the XY plane. However, you still need to turn that component on the XY plane into an X or Y coordinate. So if I were to project this triangle, this right triangle on the XY plane, it would look like this, where I have my FXY, my FX, my FY, and an angle of 30 degrees, right? And you can see it right here. Notice that my FX is in the vertical side, or vertical side on that drawing, because my 30 degree is actually an angle from the y-axis, not from the x-axis. That's the only reason I'm doing it. So, given these two right triangles, we want to find the x component, we want to find the y component. Let's go with you in the back. How do we find the x or the y component?
For the y, it would be fxy sine 30.
Okay. Like this. And what's fxy? How do we find fxy?
Take the 600 cosine 60.
Okay. How much is that? That should be 300, right? How much is 600 cosine 60?
300.
Okay, I got it right. Good. So I have fxy, just fxy, multiplied by cosine 30, and that's fy. Leslie, what is that? Fy.
259.8.
Units?
pounds.
Thank you. Hunter, can we find fx?
Yes, instead of doing cosine, we can do sine.
Okay, so it's the same expression, but with sine? Is that what you're saying? Okay. So we have fxy, sine of 30, hint, cosine of 60, sine of 30, it's just 1/2, right? So I got my fxy was 300, multiplied by 1/2, how much is that? Okay. So we found the force vector, right? Just like, your name?
Will.
Just like Will wanted. We found the force vector in Cartesian coordinates. I'm going to go back to you. What next? We found our force vector. What can we do with that? We want to find the parallel and perpendicular components to this rod. So what's next?
Position vector.
Okay, position vector from where to where?
So you want to find parallel and perpendicular?
Yes, but let's start with parallel.
Okay.
So position vector from where to where? From which point to which point? Remember, we want the force component that's parallel to this line. So what that should tell you is that we want the position vector to be along this line. So what 2 points do we have?
A to O.
Okay, A to O, is that correct? Drew, can you help that a little bit? You would say A to O. What did you say, William? Would you say A to O? Is that the position vector that we're looking for? From A to O? Change your mind?
I don't know. I can't see the.
Are we looking for the position vector from A to O?
Let's start at A.
There we go. O to A. Slight distinction, right? That would have given us the angle we wanted plus an additional, what? An additional however many degrees, 180 degrees. So we gotta be careful, okay? So we got the position vector from O to A. We got 2 minutes left to solve this problem. Remember, it's no partial credit. Either we solve it or we all get zeros. What's your name? Riley. How do I find that position vector?
It'd be the x final minus exponential, so
Okay. You can find the coordinates over there. Or, I guess I didn't write them, but.
so the first coordinate would be
-4, right?
Yep.
Or 0, which one?
-4.
Perfect. So -4i plus 4j. Uh-huh. Plus 2k. Units? Feet. Good, we found the position vector. I'm going to go back to Will again. Why? What's next? We found the position vector. What now? Got 1 minute, Will.
Well, we can do the dot product, but that's going to take us different direction.
We could do the dot product, right?
What's the use of it?
Yeah, so what else can we do that can actually skip us all the way to here? Think of Drew.
Oh, position vector. Wait.
Drew, think of Drew. What does Drew like? Unit vectors, right? Drew likes unit vectors. When you're doing your tests, think of him, okay? Just picture him in your minds, and you'll say unit vector. That's what I need to solve, okay? So I want the unit vector. Can I find my unit vector with this information?
Yeah.
Okay. Chris, help me find the unit vector. I know the unit vector is a vector divided by its magnitude, right? I have the vector, -4, 4, 2. But what about the magnitude? What is the magnitude?
The square of everything added to the square of it.
Okay, the square of everything added and then square rooted. Okay? Somebody plug those numbers into a calculator. Uh-huh.
6.
6, thank you. So the magnitude is 6. So we have negative 4 over 6. Let's just simplify a little bit more, right? That's 2/3, right? Negative 2/3. We have positive 4 over 6. That's positive 2/3. We have positive 2 over 6. How much is that? Okay. So we found our unit vector. All the way back to Will again. What's next?
7.
It's okay, it's okay. Take your time. We're already 1 minute. 1 minute behind. Come on. Will, this is your grade we're talking about. If you don't solve this,
We
you
just
get a
failed.
0. What?
We just failed. It was all or nothing.
Yeah, that's true. You all failed. Get out. No, I'm kidding. We have 4 minutes left. Let's finish this problem, okay? We found the unit vector. There's different ways of finding the projection vector. One was by taking the magnitude times cosine of the angle times the unit vector. Another way was by taking the product, the dot product, right? So we say that the parallel component of this vector is equal to the force component dotted by the unit vector. Is that correct? Of course it is. I think that's what we said, okay? So let's take that dot product. We have our force vector, Fx, Fy, Fz. We have our unit vector, Ux, Uy, Uc. Do we need to calculate the angle first, or is there any other way that we can take this dot product without worrying about the angle? How can we calculate the dot product without necessarily getting the angle? Okay, let's say that you went over time, but then you realize that the test actually gives you a 5-minute grace period. Okay, so you have just a little bit more to finish the test. And remember, it's all or nothing. And now I'm going to just go randomly. Riley, let's start with you. What's Fx? 150. What's Ux?
Negative 2/3.
Leslie, what's Fy?
259.8.
What's Uy?
2/3.
William Tyler, what's Fz? Somebody help him.
Sorry. 519.6.
What?
519.6.
What's Uz?
1/3.
Thank you. Okay, we multiply all these. Before we forget, units, pounds, times. Good. Normally in the US or English units, we call this foot pound. We say the feet first, but it's okay. Pounds times feet is also correct. But we call it foot pound. Plug all these numbers into your calculator. It's a multiple choice exam. So you plug all these numbers, make sure you get the right answer. What did you get? You. What did you get?
I got negative 100. And then 173.2.
I'm missing something here. There we go. Negative 100.
Yeah. And then 173.2.
Okay.
And then 173.2.
Forgot to multiply this by the unit vector. Look at that. There we go. All this multiplied by unit vector. All this multiplied by unit vector. What time is it? Is it time to go?
1 minute.
1 minute. Can we solve this in 1 minute? All right, let's do something interesting. I'll give 5 bonus points to the person that solves this. But you need to solve it. Like, give me all the numbers. It's probably going to be Hunter.
That's 246.4 times negative 2/3.
What else?
And then 246.4 times 2/3, and then 246.4 times 1/3.
Okay. How much does that give me? I mean, that's IJK, right? Times what? What's the last one?
246.4 times 1/3.
Okay. Thank you, Hunter. And just to put the icing on the cake, just give me the final I, J, and K components. Not for bonus, just because you like this class. Anyone, not just Hunter.
239.87.
249 point?
239.87.
239.87. Okay, what's the other one?
Oh, 239.87.
Uh-huh.
And then 82.13.
I find it a little hard to believe that 246.4 times 2 over 3 gives me 239.
164.3.
There we go, 164.3. That's a little bit better. Good. My intention here is not to rush you. It's not to stress you out. But the test is timed, right? So when you're doing the test, I want you to picture my voice just like telling you to hurry. And then I want to picture Drew thinking about unit vectors, okay? So yeah, I guess you can go. And you'll have your test. And I'll see whoever doesn't drop the class next week. Take care.